Hey everyone, welcome back to my channel. So in today's video, we'll talk about gradient descent. So gradient descent is one of the most famous optimization algorithms that we have today, and the way it works is surprisingly good, and the domain in which this is applicable is very huge. So if you understand gradient descent for one use case, you can apply the same principles in a lot of algorithms, in a lot of machine learning algorithms, even neural networks, to a great extent, and you get an amazing result by using gradient descent as an optimization technique. So this is a very important topic to understand as you start your journey for deep learning or machine learning algorithms in general. So we'll discuss gradient descent in very detail. We'll understand what gradient descent is, what are its applications, some of the common confusions that people have when they first learn about gradient descent. So let us get started. So let us first start by defining gradient descent. So gradient descent is an iterative optimization algorithm that is used in machine learning and deep learning. So basically what it means, what iterative optimization algorithm means is that this algorithm iterates upon all the training samples. So there are variants to this also, but in essence it iterates on all the training examples and then tries to optimize your parameters by finding some information from all those training samples, right? So that is why it is called an iterative optimization algorithm. Gradient descent is used to minimize the cost function of the model by finding the most optimal value of the parameters. So we have seen in our previous videos on linear classification, on linear regression, that every model has few parameters which we have to optimize to make sure our model performs very well, right? So for example, in linear regression, we had W and B as the parameters, and we were trying to find out values that are most optimal for those two parameters such that our model accuracy is the highest. So that is the goal of gradient descent, right? How do you find out those most optimal values for the model parameters? So how it does that is the algorithm calculates the gradient of the cost function with respect to the parameters and then updates the parameters in the direction of the negative gradient, right? So this is something that we'll discuss in detail, how it calculates the gradient and how it updates the parameters. But the application of this we have already seen in our previous videos, right, where we said that we did not go into the detail of how the gradient descent works or why are we exactly using these optimization algorithms, but we use those algorithms and you saw how using those algorithms made it very easy to update the parameters and then come up with the optimal parameter values for different models. So it is an iterative process, therefore this process is repeated until the cost function converges to a minimum value, like the minimum possible value, or it goes below a particular threshold, or the maximum number of iterations that you have defined, which is a parameter that you set, as exhausted. So any of these two parameters or two conditions, whichever hits first, your model stops training or your optimization stops, basically that process stops. And as I said that there are multiple variations to gradient descent, which also we'll discuss. So there is batch gradient descent, there is stochastic gradient descent, and then there is mini batch gradient descent as well, right? So we'll talk about these as well. Now, just to give you a brief introduction, these three differ primarily on the size of the data set that they use to calculate the gradient at each iteration, right? So that is the only difference that you have in all these three variations. Other than that, the basic principle or the foundational principle is the same for all of these different variations of gradient descent, right? So now, before talking about what gradient descent is or how it works, right, we define gradient descent. Now let us see what do we need for gradient descent, right? So this is something that we have already talked about a lot in our previous videos, that the things that you need is, first thing is that you need is the data. So you have an tensor, which can be an n-dimensional tensor as the input tensor, and then you have your output as a single variable or a single class or a multi-class. Then you have your model equation. So we are considering a linear regression model, which we have seen so far. So this is the equation for that model, right? Then the parameters here, which I am denoting by theta. So this is your model parameters. For example, in our case, this is w and b, right? And then finally the loss function. So loss can be any loss. It can be sum of squared losses or maybe your negative log likelihood loss. Any loss function is there. So you need the loss function as well. And then finally the gradient. Gradient is the derivative of the loss function with respect to each parameter, right? So for example, we saw that for negative log likelihood loss, which is basically minus log of p of y, we saw that the derivative with respect to w is something like this, and derivative with respect to b is where your this is your sigmoid function, right? So this is something that we have discussed in the previous video. If you have not watched that video, then I'll suggest you first watch that video. Then all this discussion will make much more sense. So these are the things that you need for gradient descent: the data, your model, your parameters, the loss function, and the gradient calculation, right? So now let us see how gradient descent works, or how the optimization actually works. So before that, we need to understand the main goal or the primary goal of optimization. So the main goal of optimization is to find out model parameters theta for which the loss is the minimum, right? That is the sole goal of our optimization, any optimization algorithm. Today we are discussing gradient descent. In future we'll discuss other optimization algorithms also, but the sole goal of optimization algorithms is to find out model parameters for which the value of your loss function is the minimum, right? That is the only goal, and that is one single principle that you should keep in mind whenever you hear the word optimization. What should come to your mind is an algorithm that tries out different parameter values and tries to find out a combination of parameters for which the loss is the minimum. That is it, right? So how gradient descent does this is, it starts by using a random initialization to your model parameters. So it starts with a random theta and then updates your parameters as part of this equation, right? Now this looks to be a very familiar equation that we have seen in linear classification problem also, and linear regression problem also. So what it basically says is, it says, for example, if we consider w as the parameter, so what this is saying is that w new is w old minus your learning rate into the gradient of your loss function with respect to w, right? So this is the exact equation that we used in a linear regression. So what gradient descent is saying is that your new parameter value is equal to the old parameter value minus the learning rate into the gradient of your loss function at that particular value, right? Or for that particular parameter. And the guarantee that this algorithm provides, and which has been empirically and can be proved mathematically also, that the loss function converges if your alpha is small enough, right? So we'll see all these cases. It's just that I'm giving you how optimization works and what is the general principle behind gradient descent. We'll discuss each of these points in detail as well. So the loss function will converge if alpha or the learning rate is small enough, right? So this is your optimization algorithm of how gradient descent actually works, right? So now let us get into the depth of it. So assume you have a let us understand what is there in this graph, right? So assume you have two axes. On x-axis you have the weight parameter, and on y-axis you have the cost parameter, right? So as we discussed in the earlier slide, the goal of the optimization or gradient descent algorithm is to minimize your cost, right? And what it has to do, it has to try out different weight values for which your cost is minimum. Now here we can see that this is a very smooth function and there is only single global minima, right? So this is the global minima, and which luckily coincides with the local minima also. So this is a very good, the most ideal function that you can expect. This is that function representation, and this is your global minima for the function. So that is your end goal. This is where we want to reach. Now If we start with an initialization which is already at the lowest point, that is the best case scenario, but that almost will never happen in a real world scenario. What will usually happen is that you will land somewhere in the in this plot. So let us assume that our random initialization places us here, right? It basically when we randomly initialize our parameters, this is where the point starts. Now the next step is I need to change my weight parameter in the direction where my cost function reduces, right? So how do you do that, right? So the one way that gradient descent says is possible to do that is that when at whatever point you are on the curve, find out the gradient of the curve at that point, right? Now if that gradient is positive, right, then what you have to do is you have to subtract the weight value by a certain quantity, right? So if this gradient is positive, this is a gradient, this is a positive gradient. If you see that it this angle will be a positive angle. So what you have to do in that case is that if your gradient is positive, then your W new is W old minus something, right? Now assume a different scenario. For example, what if we would have been here, right? Then when I would have calculated the gradient at this point, the gradient would have been negative. So in that case, what would have happened? W new, W old plus something, right? So now, since my gradient is already negative, what you can write this is as minus your gradient. So the sign is definitely coming from the gradient and we take the value of the gradient. So this becomes your update equation. Now let us keep a constant here, right? So this is the equation. So now you have your old weight. If your gradient is positive, then you have to subtract. If your gradient is negative, then you have to add. So now if this is positive, it becomes this is subtraction. Now if you make this gradient as negative, then minus and minus will become plus. So ultimately the equations that we want is something that we'll get. So this is for positive gradient, this is for negative gradient. So now we have seen what happens if our initialization places on either side of the curve. We see that this equation works in both the scenarios. So now we know in what direction we need to move, right? When we have a gradient, positive gradient, we have to reduce the weight, we have to move in this direction when we have positive gradient, which basically means that we have to reduce the weight, we have to reduce the weight value. And when we are in negative gradient, we have to move in this direction, right? Which basically means that we have to increase the weight value to some new value. So now we know the direction in which we want to move. The second thing we want to calculate is how much we have to move into that direction, right? So now that is calculated or that is controlled using something known as your learning rate, right? Learning rate. So alpha here is your learning rate. Learning rate basically tells you how big a step should you take in the direction of your gradient, right? Or negative of your gradient. So if you see these arrows here, right? So these are arrows. So why this arrow is this much long, right? Why this arrow is not, all the way towards the down, or why this arrow is not very small. So we'll see the different scenarios also. What happens if your step size is too large, or your learning rate is too large, or if its learning rate is too small. But the idea here is that this is something, again, it's a hyperparameter. There is no single value that will work best for all cases, or there is no way to which via which you can find out a value which work best for you. This is something that you have to fine tune by yourself. This is more of an art. You have to try out. There are some principles that you can keep in mind, but mostly this is an art, and you have to try out different learning rate values, and this will change based on the data set you are training, the model size, the model that you are trying to train on, and all those things. So this will continuously, this will not be a static value that you can, I cannot say that, okay, 0.1 is a learning rate and everyone can use this value, and there is no point in trying any other value. That is not the correct way. Learning rate, for some use cases you might have 0.0001 learning rate, or for some examples you might also have a learning rate of 0.5, right? So it varies a lot, and you have to find out by yourself which is the best learning rate for yourself. So now what we have covered is the two most important things to understand why gradient descent works, or what gradient descent is. First thing is, the idea of gradient descent is we need to reduce the cost function. So basically we need to reach to the minima of this curve that we see here. Now the only thing that you can do is you can change the value of the weight function, right? This is the weight parameter, something that you can change. Now to change the value of this parameter, you need two things. In what direction should you change, whether you should increase the value or decrease the value, and when you choose your increasing or decreasing the value, how much should you increase or how much should you decrease, right? So that is the two things that you need to keep in mind. Now we saw that irrespective of whether your gradient is positive or negative, this equation works if you put the gradient along with the sign. So let me write this again a little more clearly. So basically what equation comes out to be is your W new is W old minus the gradient into your learning rate, right? Now this is assuming the fact that whenever you place the gradient in this equation, you place it with sign. If it is positive, you place it positive. If it is negative, you place it as negative. Now we also see that when it is a positive gradient, you have to reduce the weight value, and if it is a negative gradient, you have to increase the weight value. So this is basically how gradient descent works, and slowly and gradually when you take steps towards the direction of reducing gradient, you ultimately will reach to a point where now there is no point in going anywhere, because if you go towards here, what will happen is, first of all, your gradient will become 0, and second thing was that you will not see any direction in which if you move, the loss function reduces. You will not see any direction, and that is your indication that everything is done and dusted. You have reached the global minima or of your function, and you are good to go. That is the lowest possible loss that your model can achieve, right? Now this is an ideal case. What happens if your function is not so smooth, right? So let me get some space here. So assume your loss function is not this smooth, and it has something like this, right? So again, this is your cost, this is your weight, and this function is something like this. Now if you see here, your function has a lot of local minimas, right? What is the local minima? Local minima is a point in the curve where if you move left, if you move right, that is the lowest point, right? No matter where you go from that point, but that is not the global minima, right? If you look at the entire function from a third party perspective, that is not the lowest point possible in that curve. For example, in this, we see that this is the global minima, right? This is the global minima, and these all are local minimas. Now, one of the main problem that gradient descent suffers from is that if by chance you get stuck in a curve with a local minima, there is no way of knowing that you're in a local minima, and there is no escape also, right? So that is a problem that gradient descent suffers from, and there is very less you can do when that happens. So how will that happen, right? So for example, when you initialize your function, so we initialized here, right? In this case, for example, if you initialize, suppose your initialization makes you land here, right? So now what will happen is your gradient descent will work fine, everything will work fine, and you will move in this direction, right? So you will move in this direction, and you will ultimately reach to this point. Now here, when you will reach, you will say that you have attained the minimum possible value of the cost function, and there is no way that you can go down, right? and that is actually not correct. But there is no way of knowing that, or there is no way of escaping from that, unless you are very lucky and you rerun your training and you reinitialize your parameters, and this time your initialization makes you land here, right? And then you come here and you reach to this function and you see that your cost function has even reduced further. But this will 99% will never happen in your practical use cases. More often than not, you'll actually end up in local minimas which are even worse, right? So that is what will happen. And uh, there is no good technique as such to avoid this pitfall, and this is something that we suffer. But irrespective of this, practically what has been seen is that gradient loss functions are not so unsmooth. They are not this much wavy in nature. And second thing is that in practicality, we have seen that gradient descent works very, very well. So these are maybe just 1% of cases where things don't go well. But this is important to understand that it is not a silver bullet. Gradient descent optimization is not a silver bullet. It has its own caveats also. So now, having understood different cases of gradient descent and how a local optima might not be the global optima always, let us go through the gradient descent algorithm, right? So this is similar to how what we saw in the last slide, which was about how optimization works. So in gradient descent algorithm, you start with a random theta, right? And for n iterations, n being a number that you choose for the number of iterations you want to run, you calculate the loss function, you calculate the gradient, and then you update the parameters based on your learning rate, right? So you calculate the loss, you calculate the gradient of the loss, and then you update the parameter. And this is the exact equation that we saw a minute earlier, where it is like the new value of your parameter is old value minus the learning rate into the gradient, right? And now we know why this equation is written like this and how this actually solves the purpose of optimizing your loss function, or basically optimizing your algorithm, your minimizing your cost function, right? So now we exactly know how this equation is constructed and why it actually works, right? So one of the things that we discussed earlier was different variations of gradient descent. So we discussed about batch gradient descent, we discussed about stochastic gradient descent, I'll just write it out as GD, and we talked about mini batch gradient descent. So let us understand each of these one by one. So now these are different flavors, as I said earlier also, that these are just different flavors of gradient descent. The underlying principle is the same, only the amount of data on which they update changes, right? So what happens in batch gradient descent is that, for example, you have a training sample of 1000 images, right, or 1000 points, and you have set your batch to be a size of 10, right? So what batch gradient descent will do is it will use the updates from all the 10 samples or the 10 training samples, and will find out the average of those 10 samples, and then will update your parameter, right? So it will take into consideration all these 10 training samples. It will calculate the weight basically already is there, and the gradient, or basically the delta with respect to the loss function, it will calculate for all the training samples for in that batch. It will take average of those and will use that average to update your parameter, or to come up with the new parameter value. So this basically takes all values in a batch. So now there are 10 values in a batch, you have 1000 samples. So basically what happens is this will run 100 times, 100 iterations will run, because you have 1000 samples. So it essentially is taking each and every example. It is taking your all 1000 examples into consideration for parameter update, right? That is your batch gradient descent. What stochastic gradient descent is that it from a batch, it takes only one sample. It will choose randomly out of these 10 samples. It will only take one sample and will update your parameter based on this one sample itself, right? What mini batch gradient descent does is that neither does it take the entire 10, neither it takes only one. It takes somewhere between this. It takes somewhere between this and uses the average of that size to update your parameter, right? So that is the only difference between these three. Now, batch gradient doesn't make sense to people because you are taking all the training examples into consideration to see how you want to move across your loss function. Stochastic gradient descent sometimes does not make sense because you have 1,000 samples and here you are only taking one sample per batch, so you are essentially only using 100 examples to update your uh, update the parameter. So how does it actually work? From 1,000 samples you're using only 100 examples to update a parameter. How does it actually work? So this again is something that has been seen empirically, that SGD, although initially fluctuates a lot, but as the number of data set or number of iterations increase, it starts to smooth out and the loss is actually as good as your batch gradient descent, or as your batch gradient descent, right? So it initially wobbles a little bit, but then it smoothens out when you train for larger iterations and when you have a very large amount of data set to train on, right? So practically it is seen that SGD performance of SGD is almost always as good as your batch gradient descent, but the time it takes to train a model using SGD is much less, because instead of calculating average for each and every example of your training sample, you are just taking one sample out of your entire batch. Now, why then mini batch came into picture? Because again, as I said, SGD requires you to have a very large data set, and only then it ensures that your data is your loss is decreasing correctly and to the lowest possible value. Sometimes when you don't have that much data, or when you don't have that much confidence on stochastic gradient descent, that is the only case where you can use mini batch also. So mini batch is something that you can set x to be 5. So you get the best of the both worlds. Neither you are calculating the average for all the values in your training samples, neither you are just using one which might be an outlier, which might not be the correct representation of your data, and all those things can happen. So that is why you can come up with a mini batch approach, right? But again, these flavors, for understanding the core concept of optimization, these flavors are not important, right? What is important is how does this equation that we have discussed actually comes into existence, right? How does this actually work? Now, when you write this equation, it should immediately click in your mind how this actually has come into existence and what is happening via this update, and where we are trying to take our pointer in a curve of the loss function, right? So this basically is your entire discussion about gradient descent. Now, one important thing that we talked about was the learning rate, right? How do you come up with a learning rate, or what are the best practices for choosing learning rate? What happens if you choose an incorrect learning rate? So we'll discuss about those scenarios also. So let us first understand what a learning rate is. Learning rate is a gradient descent. In a gradient descent is a hyperparameter. Hyperparameter meaning that you have to supply it from outside. That controls the magnitude of the parameter updates at each iteration. So by now we understand what this exactly means. Now let us see what happens if learning rate is very high. If the learning rate is too high, the parameter updates will be very large and the algorithm may overshoot the minimum of the cost function and diverge. If the learning rate is too low, the parameter updates will be too small and the algorithm may converge too slowly or get stuck in a suboptimal minima of the cost function. Therefore, choosing an appropriate learning rate is crucial to ensure fast and stable conversions to the optimal values of the parameters. Okay, so I think this is a lot of theory and it does not make sense if you do not understand it with the help of a diagram. So let us understand this with the help of a plot. Let us first take the case of learning rate too large. So what learning rate too large means is that the steps that you take are very huge, right? So for example, you are at this position and if your alpha is very large, the next step that you take, right, may take you towards this location, right? And then again you take this location and then again you take a step and you move to this location. So what will happen is you will continuously keep on flipping across these two locations because the step that you're taking is so high, so large, and you will never be able to reach the actual global minima that you are supposed to reach. So therefore alpha should not be very large. Now what is a large alpha, right? That is a question. So that is actually dependent on your use case. There is no universally large alpha. Obviously, if you have alpha very very high number, then it will not work almost in all cases, but for your specific use case, an alpha of maybe 0.5 might be very very large, and for some use cases this could be the correct alpha. So the only thing that you have to keep in mind is that if your loss is fluctuating a lot, if you're not able to converge to a minimum value of the cost function, then one potential reason for that could be a large learning rate, and you can try to dial down the learning rate a bit to see if there is a more smoother convergence possible. What happens if your learning rate is too small? Now, if suppose I keep a very very small learning rate, what will happen is that although I will move in the correct direction of my convergence, right, but I'll move very 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 slowly, right? It will take a lot of iterations to come to this point, and frankly this is very compute expensive. So if you take such small steps, it will take forever for your model to converge, right? It might not even converge before the maximum number of iterations are hit. So that is why when you see that your loss is decreasing or your cost function is decreasing, but it is decreasing very very slowly, then it might be a good indicator that you can increase your learning rate a little bit, right? That might help your model. And then finally, the case that we all want to achieve, when the learning rate is just right, where your everything is like perfect and you take good number of steps and you reach the global minima or the global optimum point in the fewest possible number of iterations and achieve the lowest possible loss, highest possible accuracy, right? This is the end goal for all machine learning models that we build, right? So this is your discussion about learning rate parameters. Learning rate is one of the most important parameters that you see, that you fine tune in deep learning models, and it is very important to understand the repercussions of having different values of learning rate and what you should do when you see a practical scenario of maybe fluctuation of loss or slow decrease in loss and all those things. So it is very handy to have these tips and tricks in mind when you optimize or fine tune your model. So I think that is it. That is what I wanted to discuss about in gradient descent. So gradient descent is a very important concept in deep learning that is used across all models or a lot of models that you will see and we'll cover together in future. So it is a very good concept to understand, and I hope this video helped you understand what gradient descent is. And when you write that gradient descent equation, now actually you will be able to visualize what actually is happening and how we are actually able to visualize, sort of reduce the parameter or optimize the parameters. Now, one thing was that we discussed this decrease in 2 dimensions because that is easier to visualize, and that is why I covered this just after a linear regression discussion. But in future, when you will have neural networks which will work in a very high dimension use cases, the general principle is the same. There is a curve and you have to reduce the value, but that curve will be in very high dimensions, so we'll not be able to visualize. That is why I wanted to just now sort of discuss about gradient descent and clear all the concepts about gradient descent. Thank you so much for watching this video. I hope you learned something. Please do not forget to like, subscribe, and subscribe to this channel and share this video, and press the bell notification icon if you like my videos. I'll keep on adding more interesting concepts about deep learning into this channel, and hopefully you can make use of them. Thank you.